Hello Professor and welcome to T04's presentation. So for our group, our main focus is implementing a smart IoT aircon system which aims to provide better sleep quality while conserving energy. How we plan to implement our system is to use an array of sensors to gather data on whether the user is asleep. Depending on the sleep state of the user, the aircon temperature will either increase or decrease. In order to detect the sleep patterns of the user, AI algorithms have been included so that the temperature can be adjusted according to the predictions made. The sensors we are using in this project are sleep detection sensor, motion sensor, and pressure sensor. There are two machine learning models used for pressure sensor and motion sensor in order to predict the sleep pattern of the user and adjust the temperature of the aircon, thus achieving the project's objective. Next, I will pass to Peter to explain more about the hardware involved in the project.
Thank you, Jeff. I'm Peter Goh, and I'll be going through the hardware of our project. For the microcontrollers, we decided to go with the Raspberry Pi and Super Mini ESP32C3. Raspberry Pi was chosen as a core hub due to its robust computational power and versatile connectivity options, making it well suited for managing complex tasks and serving as the central brain of the system. The Super Mini ESP32C3 was selected as the microcontroller for sensor integration due to its low power consumption and built-in Wi-Fi capabilities, which are essential for efficient communication within the smart home network. Additionally, its compact size offers the benefit of easy pairing with sensors, providing optimal configurability and seamless functionality within the smart home network. Moving on to the sensors, we have the pressure sensor, motion sensor, and seat sensor. The pressure sensor is utilized to detect user bed occupancy. The motion sensor is utilized to track user movement on the bed. The seat sensor is employed for discerning sleep patterns and states, including breathing and heartbeat detection. We initially contemplated on using an infrared sensor to measure user temperature, but decided against it due to time constraint. With that, I shall now pass my time on to Chenan.
Thanks, Peter. I'm Chengon and I'll be presenting software. We use Flask and MongoDB in the Raspberry Pi. The Flask is used to receive sensor data through RESTful, where the data will then be stored in MongoDB. It is also used to show the dashboard. Each sensor will have its own collection in MongoDB. There will also be a prediction collection to store the predictions. All sensor collections will be truncated once a prediction is made so as to not take up storage space. For the models, we tested KNN and decision tree since we are doing classification. Other models like GBM, random forest, and SVM were not tested due to their higher RAM usage. We chose KNN with 15 Eurosaver for pressure model. For motion model, we use decision tree with 20 max stat. I will hand over the presentation to Timothy.
Thank you, Changan. My name is Timothy, and today I'll be talking about how we set it up. So, for of the ESP32 Mini C3, we actually connect each of them to a sensor. So, for the first one is connected to motion sensor, second pressure sensor, and lastly Seat Studio. So, all these three sensors have a code that actually allows us to specify the SSID of the Wi-Fi and the password so that we can actually communicate with the Raspberry Pi. So the Raspberry Pi is actually hosting the MongoDB and the Flask. So all these sensors are actually connected to the same Wi-Fi, and we will actually send the data using the API call into the MongoDB database. And from the MongoDB database, we actually display on the dashboard at Flask. So why we use Wi-Fi is because firstly, Wi-Fi is more secure than Bluetooth. Secondly, it allows more user compared to Bluetooth. So in case we want to expand for more sensors to make the house a smart home, Wi-Fi is a more suitable protocol, communication protocol compared to Bluetooth. And lastly, it allows us to transfer large amount of data faster. Thank you, and I'll pass my time to Ben.
Thank you, Timothy. Now I'll go through our live demo. So over here we have our test subject who is sleeping. And first we have our seat sensor which determines whether the user is asleep based on their heart rate. And here we have our motion sensor which detects whether the user is stationary in the bed. And then last but not least, we have our pressure sensor, which is simulated with the finger, but in a real use case, the pressure sensor will be under the bed with the user lying over it. So with the use of these three sensors, we will produce a score with our AI to determine whether the user is asleep. And these sensor data are sent via Wi-Fi to our Raspberry Pi. So over here we have our Raspberry Pi, which has received the data from our sensors. So serial monitor is now showing the data being received in real time. And here is an example of like the motion database, the sleep database, and the pressure database. So using these data, we then use machine learning algorithm to produce a prediction of 1 or 0, with 1 representing sleeping and 0 representing awake, and we adjust the temperature accordingly as shown on the dashboard. So to sum up, our solution aims to improve sleeping quality for users whilst reducing energy consumption through the use of smart IoT solutions with the help of our AI. So our solution also ensures that non-intrusive sensors are used to ensure the user's comfort and privacy. So the principles underlying our adaptive temperature control system have the potential to transform climate management in various settings, offering personalized comfort while prioritizing energy conservation. From office spaces to like healthcare facilities, the application of our IoT solution actually extends far beyond just the smart home, showcasing the transformative power of technology in creating sustainable, comfortable environments. And with that, we conclude our presentation. Thank you for your time.